Yep, thank you very much. So my name's Ross. I'm head of simulation at BMT, or Blow Molding Technologies, and today I'm going to focus on digital twins for the sustainable packaging industry. So if you click next, and probably one more click as well. So who is BMT? So Blow Molding Technologies. And one more click. There's probably a lot of clicks, by the way, in this presentation because I've transitioned it. So forgive me if there's a lot of saying clicks, but. We're BMT, Blow Molding Technologies, and we were founded in 2011 as a spin-out from Queen's University, Belfast, and we were built off the stretch blow molding group and the polymer processing group there. So it was built on about 25 years of research predating BMT. So over the last 10 to 15 years, we've transitioned from a hardware company to, I guess, a digital solutions provider as well, and our mission really is to try and blend these digital and physical worlds together. And really our focus today will be on the stretch blow molding and bottle industry, and where I'm trying to show how we use data and simulation to effectively enable a smarter way of working. So next slide. So to start off by just showing really where is the SBM industry right now on the industrial revolution roadmap. So if we look back to the 1800s, industry 1.0 right through to, I guess, the future, which is 5.0, the human-robot collaboration. We exist somewhere between Industry 3 and Industry 4. We're not quite fully at Industry 4.0 with cyber-physical systems, but that's really where we're trying to get to. And so next slide. Really, there are 4 key challenges in the bottle industry, and I've put 4 of them here. So it's sustainability is the first one. We're trying to use a lot more recycled material. We're trying to use a lot more bio-based material to meet UK plastics packs, but it's tricky. Simply swapping new materials in and out of production lines don't work because they behave differently. Secondly, consistency is a big problem. Different geographical locations, different operators, different times of year mean that getting a consistent product, which is desirable for a brand, is tricky. Efficiency, simply use less plastic. It's not always easy. I always compare it to your holiday and you open a bottle of water and it's really thin, it fires out in your face. Not ideal. Lightweighting isn't always the best option. Rightweighting is often how it's termed, using the right amount of weight for a bottle to fulfill its functional purpose. And finally, productivity, just purely having less machine downtime, increased throughput, and being more efficient the whole way of the whole process. So really then, it begs the question, what would be our vision for a better future? So next slide. And maybe one more. Yeah, and our vision story is an interconnected future. So it's really one where no matter where you are in the world, whether it's US, whether it's Europe, whether it's China, that you have machines that are capable of talking to one another, that are able of sharing data, and that means we can get more consistent products throughout the day, across seasons, across material suppliers, etc., temperatures. And it's this really digital ecosystem, which is what we're trying to enable through a mix of our hardware offerings and our software offerings. So one more slide. Yep. Really, we need a digital twin. So I thought it'd be good just to really point out what we mean by digital twin at BMT. And I like that some of us have already shown what the definition is of a digital twin. I'm not saying this is the only one or the correct one. It's just what it means to us. So a physics-based digital replica of the bottle and how it's manufactured. For us, we needed to continually learn and update to provide near real-time insights. And finally, we want a few different layers of data fidelity. We want physical world data, we want physics-based simulation data, and then we want to layer on top of that our AI and machine learning component as well. So really, that's our vision for the future. The next half of the presentation, I'm really going to show you where we are currently and show you a lab scale demonstration of our software and our hardware talking to one another. So this is our blow scale machine. It's our unit cavity blow molder, and this is us now picking up a preform. And we're going to take this preform, we're going to take an image to capture its geometry, and then we're going to lower it down into our infrared heating oven. We're going to rotate it, and we're going to heat it uniformly in all directions. So this is probably the single most important action. Does that? Oh, the video was supposed to stop there, but something's wrong, I think. But I'll just keep going with this. So we're basically blowing in the bottle, and we will put it in the blowing station, stretch it, and blow it. You might maybe try clicking next slide, because there's a wee... Yeah, next slide again. So if you just go back to the heating. This is probably the ethos that BMT was built on. This is Lord Kelvin, and effectively he said that if you cannot measure it, you can't improve it. It's why we started out as a hardware company, as people were trying to use digital solutions, but they just did not have good enough data in. So we actually developed Thermoscan, which is a probe that allows you to measure the temperature of the preform along its length. And by having that, it's the most important parameter in how good a bottle you can produce. And really, before we start adding any layers of simulation or AI, we need to make sure we actually feed our model with good physical data. So before we even try and improve the process, let's benchmark where we are at the minute. And so that's the first point. And really what we can do when we have the internal and external temperature, we can do some inverse calculations to infer the temperature through the thickness. And then this will go on to feed our simulation model. So if you click it again, okay, I think I know what's happened. The video hasn't cropped correctly, so we're just going to have to relive the first half of this video again. So the preform one, yes, that's it blowing now. Okay. Perfect. So if we just imagine where the preform flowed into a bottle there, the next stage really is to look at the actual blowing process itself. So on the left, what I'm going to show you is our stereoscopic camera setup that shows the preform as it's blowing into the bottle shape. And on the right-hand side, I'm going to show our physics-based finite element simulation that shows we're able to capture the same sort of strain contours. So if you click one more time, it should play the video. Perfect. So left-hand side, we have a speckled pattern you'll see in the preform, and this is a common technique called digital image correlation, where we're actually tracking the movement of each of these speckles, and we're able to understand the strain field of the preform. And on the right-hand side is our corresponding physics-based simulation. Also in the cavity, we have a stretch rod, which measures the reaction force. We have the pressure measurement of the cavity. And so really what we're doing here is we want to check that our simulation matches reality in terms of pressure, in terms of force, in terms of strain. And so that's another level of fidelity. We have our physical data capture, and we now have a physics-based high-fidelity simulation that can also capture what's going on. And really, only at this point do we bring in the fancy sort of AI or ML component, only when it's grounded in real proper data. So if you click one more time, and so this is really then us layering on top of that. So our lowest level of fidelity is our real data. Our second level of fidelity is our physics-based simulation, and our third layer is really then looking at how we can start changing things like preform design, process design, temperature, etc., to help us make real-time decisions, informed adjustments, and optimal process and optimize our process. And it's this principle. It was Charles Babbage, who was a pioneer of modern computing, said good data in is good data out. And I know I'm really emphasizing it today, but you can have the best will in the world and the best machine learning model, but if it's not grounded in a few good layers of data fidelity, you can only go so far. So really that's the key message I'm trying to get across here. And with that, if you click one more time, I imagine this will bring us back to the start of the video. Yep, and if you just click again, it should. One more time. And just like that, the bottle's created. So really then we have this is our prototyping machine. It does have then the ability to print 3D prototype molds, so we can do rapid production. So basically upstairs we do our simulation work, downstairs we go ahead, we print a physical mold, and we actually then produce it. And this is what we did with Innovate UK a while ago, just to show the economy of scale that we're dealing with. By saving just half a teaspoon of plastic per bottle, over the course of 1 year, you can save about 5 double-decker bus loads and save about 100 global road trips. So it just goes to show a digital twin that allows you to optimize your process, and like with your preform, has massive implications when it comes to that sort of economy of scale, 25 million bottles per year. And so really that's what we're trying to tick off. We're helping, we're showing that we can become more sustainable. We're showing that we can have a consistent product. We're showing that we can become more efficient by lightweighting, and our productivity increases by having a process or a digital twin that allows us to adjust the process depending on the particular material or the particular bottle. So I think one more slide really just wanted to show the next step really is for us to try and scale this up, and just wanted to have a bit of appreciation for the Digital Catapult Centre. So in 2023, we actually participated in the Adoption Accelerator Programme to kick a lot of this work off, and marrying the two physical and digital worlds together. And so I'm here today, I guess, in this sort of joint initiative to show off our technology. And really going forward, I know I've used the blow molding industry as, I guess, the vessel of the digital twin, but the principles I'm showing here are very transferable, whether it's defence, whether it's maritime. This idea of grounding your digital twin in really good solid data is transferable across. And so while we are focusing right now on the stretch blow molding industry, going forward we're looking to try this technology out in other industries. So with that, that's me today. Thanks very much for your attention and welcome any questions.
Fantastic to see a real digital twin with that sensor bringing in the machine learning with the visualizations. Any surprising challenges on your journey going from blow molding technology into this more connected digital twin space?
Yeah, I'd say definitely for us, one of the hardest ones is as you start to get demands to be 95% accurate, it's exponentially more difficult to get that last 5%, that last 10%. It's very easy to get something 70%, 80%, but once you start to get, I want this to be 90 to 95% accurate, that's when, we're getting there and we're nearly there, but it's not a linear curve of getting something that's perfectly represented in terms of the time spent doing it. So I'd say, yeah, the effort required to get something really solid and really close to reality at the end is definitely something that surprised me.
And any unexpected upsides? So when you were doing it and you started to see those models coming through, anything that was surprising to the team?
Yeah, I think my initial definition of like a digital twin before I even started any of this work was just basically a process controller. And I think there's now so many more benefits like pre-actually production on the design phase. So it's like, can you use insights from your production to actually enable upstream decisions to be made? For example, can you make your preform lighter, having known that you're starting to exceed performance targets on the line, so you can actually inform upstream. It doesn't always have to be one way downstream, it can be two-way upstream.
Perfect. We've got a question that's come in. How did you validate it? I presume the it there is the digital twin.
Yes.
What were your acceptance metrics and thresholds for being decision grade, the ability to have a decision grade?
Great question. So yeah, our metrics is oftentimes a bottle will have a series of functional requirements. So for example, top load, it has to be able to withstand transport for a certain amount of top load. It has to be able to withstand, when you pick it up, a certain amount of squeeze. There are a list of functional requirements a bottle has to adhere to. So we're often driven by them. And so often we get told, can you be within 5-10% at least start? 95% is always what we aim for. If we predict something, can we actually do it within 95% is kind of our threshold. And in terms of the metrics, it's the functional requirements of the bottle, those performance tests.
Fantastic. And we saw some of the sort of meta level sustainability benefits there with the double deckers worth of buses. And but what have been the biggest business benefits for you and for BMT?
I think for us, BMT have always been a great company to support R&D endeavors. So we often do our best work with clients that speak our language. For example, clients that want to get into the data, that want to get into why. But the digital twin sometimes offers purely like a red, green light, orange light. Is production good? Is production bad? So it's opened up a space in the production world for us, and to basically have a new audience. You don't have to speak the R&D language to know your production's bad. You don't always need to know why, but we can tell you how different it is and what to do to fix it. So I would say a different industry within the blow molding. It's not just R&D, it's production. And that's why I said about the transferability of it. What we've seen, there's like lateral transfer within our industry. That's why we're potentially looking outside even the packaging industry.
And that's a great point to come in on one of the questions that we had around IP. So, looking at that transferability, increasingly collaborating with other people, how are you handling the IP around the digital twin, the work you're doing?
Yeah, good question as well. So we do have a patent around the thermoscan, for example, the device that measures temperature. That is a hardware patent. In terms of the IP, we have some of our bespoke material models are protected, or at least very difficult to replicate, if nothing else. I'd say those are two things we have patents or control over. In terms of what we will need to move beyond, for example, industry, I don't know just yet, but it is something that's at least on our radar. Like the IP, the governance, all that side of things is very much on our radar.
Perfect. And we've spoken a little bit about shifting into other areas. What's the ambition for BMT in terms of where you're going next and the opportunity that exists with this technology?
Yeah, I mean, BMT's, I guess, ethos has always been to enable a more scientific approach to, well, anything. At this point in time, it's stretch flow molding. We want to, like, decisions to be made on data, not just intuition, because we're in an industry that's very much the knowledge lives or dies with the person. It doesn't always die with, the enterprise. And so I've always been trying to enable a better way of working. It started from hardware, it's moved to digital solutions, and I guess that's really, our goal is still to go down that path. We just want, I guess, to have a widest reach as we can, and almost the inertia within the industry to overcome the status quo of, no, I have a guy or I have a girl who can do that. That's what we want to try and overcome, and we want to show that there is a different way, or potentially a more scientific way to do it.
And in your slides, you showed a global footprint of what you were trying to do. Have you been testing the digital twin about those environmental factors and different levels of humidity in factories and so on?
That's really where we're at. We have within the lab, yes, but not in terms of the scale up of. We have like used lab scale versions or representations of that, but we haven't truthfully done it in China, US, Europe to do a fair comparison. We have just done lab scale testing or lab scale environment testing. We haven't done full scale commercial rollout. That's really as far as we've got to there, is the proof of concept on our own lab scale machine. So really, we're in the next phase now.
Yeah. And kind of top 3 key learnings for someone else that was going to go on this journey, a similar sized organization?
Yes, I would say don't underestimate the amount of work that's required to get a good quality, high fidelity simulation to work. And I'm not saying that it's like our class. It's just there's an awful lot of work that goes into it. And if you're going to embark on that path, we've seen in some organizations where they just put one person and say, go bash your head off the wall until you've got it. It's not that simple. I'm sure other people in the room will say the same. You need a team. You need a team to develop the hardware, a team to develop the simulation. It can't just be left to one person in an organization because it's such a big undertaking to do a digital twin justice. So I'd say the 3 things are: don't underestimate the hardware, don't underestimate the simulation, and don't underestimate the machine learning. They are 3 discrete work packages that require dedicated effort, and bringing them all together is a challenge in itself. So it's been a big undertaking for us to get this far, and I'm sure there's still plenty to go, but I'd say looking back, it's probably bigger than even I thought at the time. And
there's a question here which I don't think it's particularly fair to ask you, but I'm going to do it anyway. What do you think the key opportunities are in Northern Ireland for digital twins? So, because you're right at the edge of some of that from a manufacturing perspective. So, what are you seeing around you from an ecosystem point of view?
Yeah, it's a good question. In my head, the biggest win, and sometimes we'll start off by just looking at by going virtual. If you're in an industry that physical testing is prohibitive, it's incredibly expensive, or it's destructive, you immediately have, you're a good candidate for virtual testing. And for all of those candidates that are good for virtual testing, I see no reason why they couldn't also be good for a digital twin technology. So if you're really struggling with physical testing, if it's destructive, if it's problematic, and you need a better way of working. So I think defense, there's obviously the 3, to be honest, the 3 sponsors that are here would benefit. I'm not just throwing it out there. I think that they're there for a reason, because they've recognized that there is a good application for this technology, because, for example, it's incredibly expensive to do a lot of the prototyping, and they're the ones that I think benefit the most. And then beyond that, I think everyone will benefit, but they'll be the key beneficiaries.
And then, as a final question for you, and then I'll stop putting you on the spot. Go ahead. Obviously, as a Catapult, so we're here at Digital Catapult. I'm from TPC. What support either would have helped you or will help you going forward? What is it that, as an SME, you really would love to see the UK's Innovation Network be able to say, BMT, we're here to help you?
I think, first of all, I'd say the funding accelerator program was great. It's a really good one to get your foot off the ground or start moving. I'd say that was definitely beneficial for us. I think some opportunities around scale up could be beneficial, and it doesn't necessarily have to be a pure funding opportunity, but it could be access to knowledge, it could be access to resources, access to people, could be beneficial, because it's not always easy. You can show the world's greatest proof of concept, but being able to fully scale it up, industrialize it, etc., isn't always easy. So I'd say that's potentially an area that could be worth exploring. I'd say that's probably the key thing, yeah.